National Data Archive on Child Abuse and Neglect.
Hello, everyone. I think I'm going to go ahead and get started while folks continue to join. Um, Welcome. Good morning. Good afternoon. No, still morning. Welcome to our archives monthly office hours. This is session number 5. And so welcome if you're returning, welcome if you're brand new. We will get started in about a minute after I go through some housekeeping. So today, our session will be 30 minutes of our LeaRn with NDACAN series, and 30 minutes or so of office hour breakout sessions with some folks with the archive. We're really excited to have you. And just for reference, if you have any questions throughout the first 30 minutes of the R training, feel free to put them in the Q&A. You can also put them in the chat or come off mute and ask Frank directly. This session is being recorded and it will be available on um, our NDACAN website, as well as all of the other recordings from past sessions. Any homeworks or assignments associated with this training is all up and available on our website. If you have any Zoom issues, feel free to reach out to us, and we can try to help you get squared away that way. Um, and I think without further ado, I will kick it over to Frank to get started with the R training.
All right. Thanks, Paige. No more ados coming your way. We're going to learn with NDACAN. I feel like I want to put some Bob Ross on and do a painting lesson or something, but let's do it. The course materials, as always, are up in our box folder. And the data that we'll be using today is the AFGARS state aggregate data 2015 to 2019. A reminder that these are all fake data sets. These are all simulated to look like the real data, but they are not real data. So please do not use them for actual analysis because your findings will be wrong. But please do request the data sets through our website if you'd like to use them. Again, all of the data, all of the code is in week 5 for today, and the slides are available in both PowerPoint and PDF on the box folder. Today, we're going to cover descriptive statistics. And before we were meeting, we were briefly discussing that some folks said, you know, the pace has been a little fast, a little slow sometimes, a little advanced, a little basic sometimes. This week, it's going to be fairly basic. I'll get to some more advanced applications at the end today, but we're really going to cover some of the basics in how we get to know our data sets in R. And I want to cover, first, we're going to use the AFGARS agreg suppressed.csv file. And again, this is simulated fake data, but what it represents is counts of children in foster care by US state. So, basic descriptive statistics in R. When I think of descriptive statistics, I tend to think in a couple categories. The first is measures of central tendency, right? And the mean is our old trusty favorite. And in R, to compute a mean of a vector, we use the mean function. Again, in R, we're typically going to organize our data sets into data frames where each column and row can be thought of as a vector. So for example, if I had my AFGARS data loaded in as AFGARS, and I wanted to compute the mean number of entries in a state or across states over time, then I could compute mean AFGARS $sign to index my data frame, and then entered would be the name of the variable, and that would return the average number of entries in a state and year. Sometimes you may want to be fancy and compute the mean yourself, and that's just going to be sum of x over length of x. These functions I tend to refer to as summarizing functions. That is, they take as input a vector, a numeric vector in this case, and return as output a single number. That is, they reduce the dimension of it. They take a vector of, say, 100 values and in return provide one summary statistic. And the mean is going to tell us about the average point in that vector. Sometimes when we have distributions that are not symmetric, the mean, though, is not the best measure of central tendency. Means, as we all know, are highly sensitive to outliers. And so in a lot of cases, what we'll see when we look at these administrative data is we'll see distributions of our variables that might have quite long tails. For example, if we're looking at foster care entries, we're going to have a substantially long right-hand tail because some states have larger populations than others and have larger numbers of children entering foster care than others. So the mean might not give us the most informative measure of central tendency. In that case, the median can be more useful, and the median function in R will return the value at the 0.5 quantile of the data. So median of a vector gives us the 0.5 quantile of the data. That is, it gives us, if we arrange the data from its minimum to its maximum, the data point that's exactly in the middle. If we want to, again, if you want to be a little more tedious about it, you can compute it as quantile of a vector, comma 0.5. The quantile function is more generic than median. With the quantile function, we can return any quantile of the data. We could, take the 2.5 quantile, the 97.5 quantile. We can go anywhere we want with that. The second category I tend to think of is dispersion. So we have central tendency, and mean and median are best there. For dispersion, we're measuring how spread out the data are. How much variation do we have in the data? The standard deviation is computed simply with SD. So if we provide a vector X, we can do SDX. And typically how you're going to use this in R is with, again, data frame indexing. So it'll be SD, AFCARS, $, the name of your variable, right? And the variance is simply the square of the standard deviation. So we don't necessarily need a separate function for it. We could just type SD of X squared, but we can also compute it directly with var parentheses X. Sometimes we might want something like the interquartile range. We might want to know where is the central 50% of the data, or where is the central 80% of the data. And in that case, the quantile function is very useful. Again, we can use the quantile function, provide as input a vector. I'm just calling it X here, but it'll typically be, again, something like AFCARS $ entered. And the nice thing about quantile is I can actually give it a vector of values between 0 and 1, and it will return to me all of the quantiles for the specified intervals, right? So in this case, I'm asking for the 25th and 75th quantile. That'll give me the middle 50% of the data. But there's no reason I couldn't add 5 more values in there. I could ask for the 0.01, the 0.1, the 0.25, the 0.75, the 0.9, the 0.99, right? I could ask for those all at once, and R would happily return to me 5 or 6 values. Minimum and maximum are also quite useful, and they are quite simply min and max. Now, those are what we'll use for continuous measures. When we have categorical measures, then crosstabs are incredibly useful, right? For bivariate crosstabs, in a data frame, we'll just use the table function. Table, where I provide table with 2 vectors, and it will provide me with a simple crosstab. If I want a univariate crosstab, I can provide table a single measure. But table's really useful when I just want to look at frequencies across a categorical variable. But when I want to do something more advanced, or I want to do a multi-dimensional crosstab with more than one grouping, grouping variable, I'll often use the group by summarize syntax that we covered in our introduction to the tidyverse. And I'll show you how that works a bit when we get to the code demonstration in a moment. So group by summarize will do something similar to table. It will provide us with cross tabulations if we set that up correctly. But table is when you want a very simple univariate or bivariate crosstab, table is your go-to. Now, R understands that many of us want to just see a lot of descriptive statistics on our data at once. And so the summary function is a very, very handy tool. If we provide within summary a data frame, what R will do is it will compute the minimum, the maximum, the interquartile range, the mean and the median, I believe. So it'll provide you with that kind of slate of descriptive statistics that we all know and love, but it will do it for every variable in a data frame. So if you want to just get a quick glance at descriptive statistics across your data, summary on a data frame is a very good way to do that. So without further ado, let's hop on to RStudio for the rest of our time together today.
The program, written in R, is included in the downloadable files for the slides and the transcript.
All right, let's get started. This is up on the box folder as week5.r. You'll notice that I put this chunk of comments at the top of my code. I like to do this with all of my code. I have a sort of template I like to use for my code documentation. You can actually program macros into RStudio to do this automatically, which is pretty cool. But it's a really good idea to document the heck out of your code, especially when you start working across lots of projects. This way, anytime I open up a script, I know exactly what it's for. And if I'm collaborating, I know who has touched it last. As always, we're going to start by pulling tidyverse in. And I'm going to execute this sequentially. But I could click the source button up here to run the entire script. And a lot of times that's what we're going to want to do. For teaching purposes today, I'm going to run it line by line. So I'm going to highlight line 7. I'm on a Mac, so I'm going to push Command Return. On a PC, it would be Control Enter to run tidyverse and go ahead and get that in. And then we're going to run the AFCARS demo read function with the read_CSV. You'll notice that I did not specify a full file path here. And the reason I don't have to do that is because I'm using an RStudio project. We talked a little bit about this in our data management session, but I strongly recommend that you learn and use how to work with RStudio projects because it makes relative paths something that's baked into your programming environment. It makes your life a lot easier. So in this case, I have a subdirectory in my LeaRn folder called data that contains all of my data files. So let's show how some of these functions work in base R. And I like to distinguish between base R, that is the functions that you get with R without loading any external packages. And then I'll show you some of the tidyverse approaches that we can use. So mean, we're going to look at exits today. So I ask R to provide me with the mean of the exited variable, and oops, I get an NA returned. Well, part of the problem there is that I have some NAs in my exited column. My apologies, that doesn't show you everything you want to see. So let me use the glimpse function from tidyverse to show all of the variables. If we look at exited, we can see in row 3, and then again in 4, 5, 6, 7, we have NA values. And anytime R tries to compute something, a numeric quantity over a vector in this case a column that contains missing values, it will return a missing. That is, it cannot compute numerically what the mean of a vector with a missing value, and it is. So we need to be explicit that we want R to remove those missing values when it does the calculation. This does not remove them from the data frame. It simply removes them from the calculation of the mean. So let's see what we get now. All right, it's no longer missing. It's 365.8, right? So we have on average for these states, and I like to think of our data here as being at a state and year unit of analysis. That is, each observation represents the total number of cases in each state for each year. We have multiple years represented in this data. So the average state year in this data saw 365.8 foster care exits. How many missing values are there in exits? Table is a great tool to use here, and we can nest within our table call the is.na function. What is.na does is it returns us a vector of true and falses after it evaluates the variable exited, so that all values that are missing will return a true, and all values that are non-missing will return a false. Table will tell us how many trues and falses we have in that vector. So in exited, we have 1,023 missing values, 3,077 non-missing values. So about 1 in 4 of our observations are missing in this vector. That's a pretty high proportion of missing data. The actual AFCARS data, if you're working from it, will not have this much missing data in it. It will have missing data on some variables that is this high, but not on exited. On some of the variables, you will experience very high levels of missingness. And we have talked about in some of our previous training sessions and are likely to talk again in the future about how we recommend handling those missing values. Okay, for now, we're just going to do na.rm because we just want to compute things. So we computed a mean of 365, but again, we talked about the fact that a lot of these distributions are not symmetric and might have outliers, might have substantial outliers. In this case, the median reveals that right away. We saw a mean of 365.8, but a median of 106, which tells us that we have a lot of mass at low values of exits and a few observations with incredibly high numbers of exits that are pulling that mean up. So in this case, the mean and median are telling us something quite different. And depending on what our goal is for summarizing central tendency, we might want to be very aware of those differences. All right, so we know we've got substantial variation in this data already based on those mean and median numbers, but let's quantify exactly how much it is. Our standard deviation is 686. That is, on average, the average observation differs 686 from the mean. That's a really high level of variation when our mean is 365, right? The variance is obviously going to be dramatically larger than that because it's the square of the standard deviation. Might not be as directly informative in this case, but it's still useful to know how to calculate. So let's check out the range of the data. We have this variable has tremendous variation in it. We can see that already. The minimum value is 0. So we have some state years in this data that report no foster care exits. And our max is 7,722, right? So we've got a tremendous range here. And we can see now how we would end up with a standard deviation that's that high. What's our interquartile range? Let's think some more about quantifying the range of the data. Okay, so we have a fair amount of mass. That is 25% of the data lies between 0 and 22. We know the minimum is 0, right? So the 0th quantile is at 0, and the 25th percentile or 25th quantile is at 22. So 1/4 of the observations fall between 0 and 22. And then again, another 1/4 of the observations fall between 403 and 7,700. Where half of the observations fall between 22 and 403. Maybe I want a broader interval, right? That 50% interval tells us a lot, but maybe I just want to know something like, where is most of the data really? Where's 90% of the data? Let's drop those outliers and see where most of the data is. Okay, we still end up with a 0. So those zeros are not that uncommon here. We have 5% of the observations at least are at 0. And the 95th percentile of the data is 1583. So this gives us a bit more information about where 90% of the data is. We're excluding now all but the most extreme observations. Let's see what our state and year coverage looks like with a crosstab. So now I'm just going to run a univariate crosstab on FY, which is our fiscal year. And this will tell us how much data we've got for each year. In this case, we have, about 820 observations for each year, but it's not consistent. And so this is telling us, actually, this must be reported at the county level and not the state level, because we don't have several hundred states. Whatever, it's simulated data. This shouldn't look right, and it doesn't, because you would immediately think if I'm looking at state year data, I should have 50 or maybe 51 or maybe 52 observations if I'm including Washington, D.C. and Puerto Rico, which are often reported in the data, but I should not have 819. If I saw this, I would immediately start to wonder what was going on and go back to square one and look at my data structure and make sure I processed things appropriately. In this case, we'll just let it slide. And then let's check out our state coverage. All right, I'm seeing 79 observations for state 1, which again is a little strange given that we have 1, 2, 3, 4, 5 years of data. I should expect to see 5s for all of these categories if we had what we would call a balanced data set. When we are often we'll refer to these time and place data sets, that is repeated measures of the same units over time, as panel data. And we often distinguish between balanced panels, where we have the same number of observations for every unit, and unbalanced panels, where we have differing numbers of observations for each unit. In this case, we have an unbalanced panel. We do not have the same amount of information for each unit. So let's check on our missing data by exits over time. Now I'm going to return to my is.na formulation for exited, but now I want to know, is there more missing data over different years of the data? So I'm going to do a bivariate crosstab, where effectively I'm going to ask R to compute how many values are missing for each year. And in this case, I can see that I have the most missing data in 2019, the least missing data in 2015 and 2017. Okay, so what if I want the mean exits for each year? Now we're getting a little advanced. Let's pivot over to the tidyverse. The anatomy of the tidyverse calls are such that I start with the name of my object. It's almost always going to be a data frame, or what tidyverse may call a tibble, which is just their precious name for a data frame. It'll work the same way 99.9% of the time. So I'm going to start with my data frame, Afkar's demo, which we have been using the whole way through. And then this little operator is called a pipe. It reads, if we're reading the code, we would read this line 52 as take Afkar's demo and then. The pipe effectively means and then do the next thing. So I'm saying take Afkar's demo and then group it by fiscal year, and then summarize a new variable called exited that will take on the value of the mean of exited after removing missings for each fiscal year. So let's see what we get now. Now I can compute the average exits over time, and we don't have a whole lot of variation in the mean exits, despite having tremendous variation in the untransformed exit counts, right? We could also set up a summarize with multiple variables, right? So after I've got my group by FY, I can use summarize to define multiple summary outputs. In this case, I might want to compute the mean of exits and the median of exits over time. And I can return that as a single object. So now I have FY, exited mean, exited median. Well, we've gone that far. Let's add standard deviations to the mix. Now I might have a descriptive table that's ready for me to put into a report. If someone wants to know something about the mean exits, median exits, and standard deviation exits over time, I have that, and I could use, for example, the KABLE, the cable function provided by Knitter, to provide me with a markdown table output that could go straight into a markdown document and make a nice report. But maybe we don't want to go through all that trouble. We could just use summary. Summary of Afkar's demo will understand whether we have a numeric or a character or a factor variable. And again, it will provide us with descriptive statistics for every single measure in the data. It'll also count the missing values for us for numeric variables. Sex here is a character variable, so we're not getting any information on that. If we converted it to a factor, we would get a category count. And it doesn't make much sense to take like the mean of state because it's an identifier. But numchild right, exited, we can see we're returning a lot of the output that we just spent a lot of time computing. So summary can be really useful for just taking a quick glance at all of these descriptive statistics. But my typical preferred approach is something like this, where I can drill down and really focus on exactly what it is that I want to know for particular sets of measures. That's all I've got for y'all today. Homework is posted if you would like some practice. I've given you a few challenges that you can use this data to play around with and see if you've mastered the tools. So yeah, I'll open it up for questions before we pivot to the second half of our program.
Yeah, I don't see any questions coming in on the chat.
No, that's great. We covered a lot of the tidyverse approaches here earlier, and so seeing this again is helpful. These really do map onto, I like to think of those, the mean, the SD, all of these as summarizing functions, these collapsing functions that reduce dimension. This group by summarize is a very, very good way to approach those kinds of questions. Sorry, Paige, I cut you off because I just like talking so much.
No worries. Yeah, no, I think we can move to office hours, and if folks do have questions, y'all can stay and join Frank or Alex's room to ask about anything we just talked about, as well as other things too. So we will transition over to our typical office hours setup. So
I
on.
also wanted to make a quick announcement that the Summer Research Institute applications are open and are due on March 1st. And so for those of you who are not familiar with the Summer Research Institute, it's a competitive application-based program where folks submit kind of a research idea of something that they want to do. You know, we have a lot of grad students, postdocs, early career folks, but also folks come from across the career spectrum. And if accepted, you work closely with staff over about 4 days to move your idea from familiarity with the data and a strong research question to hopefully having the analyses done. And so if you are interested in using the data or you have an idea, but you might need a little support in executing the idea, I highly recommend checking it out. And you are welcome to pop into my breakout room to discuss it if that's of interest.
Cool. So now we're going to switch over to breakout rooms.
The National Data Archive on Child Abuse and Neglect is a joint project of Duke University, Cornell University, University of California, San Francisco, and Mathematica. Funding for NDACAN is provided by the Children's Bureau, an office of the Administration for Children and Families.